Hi, hi, hello. Happy Tuesday. Happy Learning Teaching Tuesday. Hope you're doing well, Ash. I'm alright. Hi, Perry. Thanks for throwing stuff at me. Nice to see y'all again. Nice to hang out again. Ugh, today has been a sleepy, eepy day for me. Eepy. I had to wake up earlier than normal because I had some training for work. I don't know why I signed up to do it, but I had training to do some like cost management stuff for work. I thought it would at least be like a little bit interesting. It was not. So I woke up early, called into the Zoom meeting from in the office. I probably should have stayed home and worked from home, but I called to the Zoom meeting from in the office, and I immediately started zoning out because they did not have anything interesting to say at all. Didn't have anything interesting to say at all. The money stuff is so boring, and they use all these acronyms, and they say all these silly things, and couldn't be me. I plan on taking none of those work tasks ever. You're doing good now that I'm here. Well, that's a given, right? That's a given. I'm always gonna make your day better no matter how it was before. It could have been good before, but now it'll be great. Or it could have been great before, and now it'll be fantastic. Or it could have been piss poor before, but now it'll be good. It'll always be better with me, right? Right? Right, chat? Right, chat? You woke up for a 9 a.m. meeting that was canceled 2 hours...
Everything is better with Belle.
Ooh. 2-hour meeting notice is, I mean, I would definitely prefer to have it 2 hours before it canceled than get a call and be like, oh yeah, there's a meeting in 2 hours. Hi, Mystery. How are you? Has your Tuesday been good? Is school treating you well? Hold on, one sec. I need to adjust my headband. Do. Okie dokie. Do. So anyway, I mean today I really wanted to play more of that Turing Complete game. The one about building the computer processor, because I was having a lot of fun with it last week, and I'd like to do more of that today, because that's still pretty educational, that's still pretty interesting, but this week I want to be better. This week I want to really try and nail down the idea of using less devices and less fan out and having less parasitic capacitance. So we're gonna try and be as efficient as possible today. Be real optimal instead of that mess of a million gates we had last week. Learn about CLN optimization. One second. Google has failed me. What does CLN stand for? Nail you down, Ash? Huh? I normally try not to use the nails. Those sound pretty painful. Maybe the chains, maybe some rope, maybe some zip ties. I think those get you a lot of the way there. Zip ties, you just have to be careful not to cut off circulation. Combinational logic now. Oh! Okay. Interesting. One second. Do. interesting. Very interesting. I do know some stuff about optimization for gates. Let's see. Do I have my handy dandy drawing tablet? 1 second. 1 second. Bump, 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 bump. Do. I also realized that whenever I sing along to the tune, I have a delay on my audio to match my model, so it probably does not sound in time with the tune at all. I need to show you. Why do I need to show you? Huh? Huh? Are you not paying attention in class, Mystery? Are you not paying enough attention in class? Not paying attention to your lectures? It's okay. You'll give me 5 seconds. 5 seconds is all I need. What? Huh? I mean... It's all your dad needed. Do 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 do. Do 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 do. Bum bump. It's this one and this one. Do 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 do. Do 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 do. Boom. Okie dokie. Artichokey. Ahi pokey. Can you guys see? Said the blind man as he picked up his hammer and saw. As he picked up his hammer and saw. Okay. Oh. I always forget to set a new layer. Okay. New layer set. Boom, boom, boom. Okay. So, Mystery, what do you know about logic gates? I will say I don't know too much about optimizing the logical layouts of them, but I understand physically. So it's an let's do an inverter. Because I think the inverter is a very standard thing to do. Let's see. It's 1 MOSFET, 2 MOSFETs. I'm trying to remember what the symbol for the right type is. One of these is P-type and one of them is N-type. I just can't remember which one's which and which symbol it is. But just know that one of them, they are different types. But all that you need to know about the different types is that one of them specializes in pulling voltages up, and one of them specializes in pulling voltages down, right? So one goes to VDD, and the other goes to ground. Do. Okay? And I think this is a lot of this will be callbacks to what I talked about with my digital signals video and the talk I did about memory way back. Must be months ago now. Okay, so the idea is that you put in signals. Oh wait, whoops. With the inverter, you only have 1 signal. But you put in a signal here. That signal gets connected to I think the term is gate for MOSFETs. It's this piece of metal on the transistor. And if you aren't familiar with how field effect transistors work, what they are is essentially, it's like there's some material here on one side that's conductive of metal, and then there's some material here on the other side that's conductive or metal. I think it might actually not. I think it might actually be doped silicon or something of the sort. I can't remember the exact details. But one side is what's called the source, and the other side is what's called the drain. And then what I just talked about is the actual metal that goes like here. There's an insulator in between. And then there's a bunch of semiconductive material that bridges the gap between these two conductive parts, okay? So, what happens is, when we put charge into, or pull charge out of, like, the gate, right, this metal part, I think it's called, man, I need to really quickly check so I can use the right words. Yeah, it is called the gate. Okay. So when we put, say this is the type that turns on when we give it negative voltage. So we pump electrons in. What that's going to do is it's going to build up a bunch of electrons on the gate, because it's really negatively charged. And then all that magnetic field from the electrons on the gate is going to not necessarily move protons or positive charges, but like it pushes electrons away. And essentially what it does is it pulls positive charge out from the source and into that area of semiconductor. And once it pulls enough to bridge this gap, then the middle part is conductive, right? So what we do is we charge up the gate with a bunch of electrons that fills this gap with conductive charges, and then charge can flow from the source to the drain, okay? And like I said, that was the type that would turn on with a really low voltage. The other type does the exact same thing, but it turns on with high voltage. It turns on from positive charge instead. Okay. So what you should notice about this is that, like I said, there's which color to use? There's metal on this side, or conductive material on this side, and there's also conductive material on this side. And there's conductive material here. Okay? Now then, how these work, like I said, is they allow charge to pass through them. So when we want to set a gate output, like say we want this inverter to output high, what we need to do is we need to connect the high side, VDD, to the output. So we need to turn on this transistor to allow charge to flow in. Technically it's electrons flowing, so it's technically electrons flowing that way, but with current we normally use the conventional description for current, which is going from high to low. So that's like from VDD down into the endpoint. So that's turning on this transistor, okay? If we wanted our logic gate to output low, the exact opposite, this one looked like a... Thanks, Penboo. I didn't see it before, but I see it now. If we want it to output low, it of course is the exact other side doing the same thing, where we need to connect to ground to the output, and then the charge flows to ground. It gets grounded. Okay? So in terms of timing optimization, okay, there's two things that really are what decide how fast this process happens, right? Because what this is, the output is a piece of metal. Again, it holds a bunch of charge. So the more capacitance it has, and the more charge it needs to hold, then the more we need to flow into or out of it, right? So if it's really high capacitance and we want to charge it up, we need to flow a ton of current. Not necessarily like a ton, but we need to flow more current than if it were low capacitance. Okay? So that's thing number one, which is capacitance of the output. Thing number two is how fast can we flow that current? So how fast can we flow? When we short things, I mean, we sort of count it as instantaneous, but that's not really what it is. There's resistance there. That resistance comes from the transistor. Okay? So how do we know how much resistance a transistor has? Well, it's not necessarily something that we generally quantify in terms of pure resistance, but we know how we can make it more or less resistive. Okay. Hi, Prue. You won't. Are you sure? Are you sure? Is that a promise? Do you want to sign the contract? What's the difference between current and voltage? That's... Okay, I mean, that's like a different sort of question. And how I liken it is to water, where voltage is water pressure and current is water flowing, which again is weird. But anyway, resistance of the transistor, that's second thing. I don't know why I did capacitance just C and then started writing out resistance. But how we change the capacitance, or not, words hard, how we change the resistance is we make the transistor bigger. We like physically just, instead of it being this, we like literally just beef up everything. And that, by making everything thicker, first reduces resistance, but it also reduces resistance because by making this capacitor gate piece bigger, it also means we can store more charge, and that pulls like a sort of stronger electric field, right? But there's a downside to this. This reduces the resistance, but we've also made everything bigger. So remember how I talked about how there's metal here, and there's metal here, and there's metal here? Well, when we made it bigger, we added more metal, and that increased the capacitance, right? So if we make this plate 2 times as big, it's going to have 2 times as much capacitance, and we're going to need 2 times as much charge to trigger it. Same with here, which would be the drain, which would be connected to the output, right? So that's literally a piece of metal here that we make bigger if we're making the device bigger, which means that this whole continuous part now has higher capacitance. So we have to be careful with how big we make these transistors in order to balance how much capacitance we give the output with how much resistance the transistor has. Yes, Mystery, sometimes it is better to be smaller. It's really interesting because while it's easy to like think about here in this scope, what really matters is you have to remember that, of course, you're not building only a device. In your network, you're probably going to have multiple devices that go together. Maybe to an AND gate, right? And this AND gate might go to several different gates, right? So, in order to optimize this, we need to look at the entire thing, first of all. And it matters because when we choose a size for one component, when we're choosing the transistor size in here, for these transistors, oops. The capacitance for the gates is something we talked about, is also linked with the capacitance of the output of the gate before it, right? And then the capacitance of the drains that we talked about, which is like these guys, is also linked with the capacitance of the gate for the logic gate after it. So you need to optimize with that level of capacitance in mind. So if this has really big fan out, right, like this one, it goes to a lot of other logic gates. We call it fan out because it's like fanning out from 1 to 3 in this case. And you have a bunch of capacitance from these other guys. If you have a bunch of capacitance from those other guys, then it sort of doesn't matter if we add a little bit of capacitance here, right? If we add a little bit more capacitance here, it doesn't matter because in the grand scheme, most of the capacitance comes from the other guys. So in that case, since it doesn't matter that we add some capacitance here, it's better to make these gates bigger. It's better to make these gates bigger, you add a little bit more capacitance, but in exchange, you add a lot of current by reducing the resistance on those transistors. So that's how delay on these guys works, is at a basic level, every gate's delay individually is just simulated as a resistance to a capacitance, right? And it's just the delay time comes from how fast we can push the current into the capacitor to charge it up or discharge it. But that capacitance changes based on what you hook it up to and what size transistors you have in there. And the resistance changes based on what size transistors you have in there. So anyway, that's the quick spiel on what really gets done in the quote-unquote optimization of logic gate speeds. There's nothing, this does not at all involve the different formations you'd put them in to have different logics. That is its own thing. This is a level of optimization that has to happen after you have your architectures sorted out, right? So after you know what sort of logic you want, after you've planned out how your AND or OR gates or whatever, or inverters, after you've planned out your network, then you do stuff like this, where you start doing computer-based analysis is really how this is done. Because of course, it is like pretty wild to do crazy levels of multiple variables changing. So people normally use computer-aided design software. I'm sorry, guys. I'm sorry. I'm not sure if there's... I probably could have explained it better. But... but I was not entirely, like, prepping to do a lesson on this today. I was just sort of thinking... I did sort of think about this when I was like, oh yeah, I want to play more Turing Complete on Tuesday. Maybe I can talk about this. But there's like crazy math involved where basically what you're doing is you're like looking at what you anticipate the entire delay to be, and that's from like adding the delays of everything within it. And then there's like what you're supposed to do is you're supposed to try and make every stage, like this is a stage, this is a stage, this is a stage. You're supposed to make all of them. I think the optimal way is to make them all the same amount of delay, roughly, if I remember right. There's some, like, wild nuance to this. Yeah, I remember when I learned this in school, over a year ago. Honestly, it wasn't that long ago. It was like a year and a half ago. So I should probably know it better. The math was intense. But it wasn't even like calculus intense. It was just, there's like numbers all over the place. It was like mainly algebra and maybe some like exponential or logarithmic stuff, but like it was it was not exactly the most pleasant of math experiences for me. But I don't know, if you guys didn't understand it, then I mean I can try and help illuminate whatever you didn't understand. But I know it's a sort of tough concept to think about and visualize. In the meantime, let me open Turing Complete. Where is it? Ba, 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 ba. Yeah, Gojo. Tedious math is the right set of words for it. You guys can see, right? Where were we? Where did we leave? I think when we left off, this guy. Oh no. How do I go back? It was this guy that we had like the big mega mess of wires. That thanks to some homework done outside of stream and some persuasive suggestions from Penbu, we figured out there was learning about how this could have been way fewer gates, and I would like for future answers to be way fewer gates. So the name of the game today is to be better. Okay, what's our next level? We measure the universe with numbers, so your machine must learn to count. Okay. Treat the inputs as 0 or 1 depending on if they are red or green. Add them together in binary such that the result is either 0 or 1. As with normal addition, the result cannot be described with one digit. Set the carry to 1. Okay. So this is the half adder that did get mentioned. So the idea is you're going to have what's called a carry. A carry is alright. So when you add stuff, if you add like a 3-digit number, right? What you start by doing is you add the ones column. And if the ones column adds up to something over 10, then what you do is you quote unquote carry from the ones to the tens column. Okay? Yes, a car. Yes, a car. We literally just created a car. You're gonna carry me? Okay, so the idea is in binary, when you add it up, you should have a carry if it adds to 2, right? Because binary is base 2 instead of base 10. So that's really easy. That just means both of them are on. So you'll have a carry when both are on, which means it's an AND gate. The sum is what stays in the column. So when you add 3-digit numbers, right, in your ones column, you end up with a sum for the ones column. If you add 2 and 6, your sum in the ones column is 8. Sorry. Girl math moment where I was like, what's 2 and 6? So the sum is what stays in the column, right? In this example, it can either end up with a 0 or it can end up with a 1, because that's all you can have in binary, right? So for that, we use exclusive OR. Exclusive OR will give us 1 when the sum should be 1. The sum should only ever be 1 if only one input is on, right? If neither input is on, the sum should be 0 because we've added nothing in that column. And if both are on, the sum should be 0 again because it should all go to the carry. So this is what Penbu was talking about. It's the half adder. If you don't know why it's called the half adder, it's because this is the very beginning of the chain. It's only there are no carries involved in this. In the future, I'm sure we'll have to build the full adder, which is the half adder, but also has the input of a carry. Okay? So anyway, that's the two parts of the half adder are the exclusive OR, which gives the sum, and the AND, which gives the carry. Where's the button to play it? Where's the button to play it? I forget. Okay. Easy. What's this one? Introduces the delay line component. It's an input and it takes outputs. Okay. What I was just talking about before we started the game, I was talking about the delay from gates. Okay? We do have times where we need gates intentionally to be slow. Okay? There's a lot of really interesting stuff about timings, about logic timings. And the idea sort of is that... Oh, this is boring. I wish I had more gates. But we'll pretend that they're different gates here, right? We'll pretend that they're inverters. Okay, the idea is that if you need to do some logic to a line that passes it through... Oops. That passes it through 3 gates, right? And then you also need to do some other logic from the same signal. Stop. Okay. That does the same logic to the same or a different logic to the same signal, but it only passes through 1 gate, and then something else needs to read them both. You need to make sure that your signals get read at the same time, right? So this gate, this line, which has to pass through 3 gates, seems like it would be slower, and it would get there significantly later than what goes through the bottom. Sometimes that'll mess things up. So what you do is you intentionally add delay to the bottom line so that they get there at the right time. Okay. Back to clearing the stage, which I guess is literally just putting delay on. It looks like, from reading it, the delay is not 1 but 2. Just because this green is not 1 after but 2 after. So let's try it. Ba 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 ba. Heck yeah! Have you guys seen the videos? The video of Gargura not being able to add negative numbers? Or not being able to subtract that and result in negative numbers? Alright. Input and output of this level are using bytes instead of bits. One of 2 new components you are given takes a byte and splits it into bits. Frick. A byte is 8 bits. Fun fact, half a byte is 4 bits. That's called a nibble. That's called a nibble. Isn't it so cute? Why are programmer terms so cute? Why are mechanical engineer terms not cute? Huh? Programmer terms have stuff like nibbles and bugs and glitches. It all sounds so cute. Mechanical engineering terms are like fatigue, ultimate tensile stress. I wish we had more cute words in mechanical engineering. I don't want to talk about creep. Okay, double the number. Byte splitter splits it into 8 bits. Oh. Okay, so these are actually like the byte. Is bus the right word? Bus being like multiple lines put together, because like, you know, a bus carries multiple people. If you want to double the value of a bit, all you do is you move it to the next line in binary, right? Because the next line will be double. So I guess that's what we're gonna do, and see if that's the right answer. I mean, I think this is... Oh. I wish it gave me more of a heads up when it was gonna trigger it. Fuck! 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 I did it again! I did it again! I accidentally clicked again after I triggered a win. Ah! Okay. 1, 2, 3, 4, 5, 6, 206. Are you done? Are you done? You're going to trigger any time now, so I'm going really, really slow. Waiting for you to give me the win condition. Okay. Maybe they were cute 400 years ago? Are you calling me old? You bench? You bench? I'm not that much of a hack. Do y'all think if you hanged your username to certified... Oh, changed your username to certified bench? I get... I'm starting to realize I should do that thing that... that they do where they read the message in their brain first before saying it out loud. Alright, in the previous level we added 2 inputs. Now we'll add 3. Okay, here's what we were talking about. The half adder. Thank you for the cat mode, Gojo. Nya, nya, nya. Okay, so the half adder added 2 inputs because it's just the 2 digits getting added. Now we have the full adder, which has to add 3 inputs. How do we do this? Let me think. So, we're gonna start by doing this in a way that I'm sure makes sense, but will probably have too many gates. Okay? So the carry will for sure be lit if any combination of the two inputs is on, right? Because then you'll have at least 2, and that means you'll be forced to carry one to the next tier. So that solves our carry. What our sum needs, when our sum needs to light, is our sum needs to light when exactly 1 or all 3 are on. Whoops. I fricked this up. I fricked this up. It needs to be triple OR. Triple OR. That's for the carries, because it's the OR of any of these ANDs. Okay, so one condition for our sum will be that all of these ANDs are lit up, which means... I guess I could do outputs from these, or I could just do the triple AND direct. So that is one way to light up the sum. The other way to light up the sum is... what will tell us if only one of these is lit? My heart says we should use some version of XOR. You're so not an intelligence build. It's okay. It's okay. It's okay to be a charisma build. So XOR between the top two will tell us if one of the top two is lit, and only one of the top two is lit. And then for the bottom one, we can use a NOT. And then we can XOR again, I think. Right? Because if the bottom one is lit, and both the top are not lit, actually, I think this can go straight without the AND gate. We can kill this AND gate. Let me quickly play through. Nope. Okay. Current sum. Oh, okay. I see what I messed up. You like the music that's playing? That's good. It's just the background music from the game. So this tells us if only one on the top was lit. How do we add in the bottom one? Way to tell if only one is lit. We could use 2 XORs? That will light if only one is lit. And then the bottom will light if only one is lit. Then we'd have to re-add the triple AND from before. You say mechanical engineering is way older than computer engineering, which I guess is true, but I think the terms we use in mechanical engineering... I guess the terms we use might be old. I don't know. I don't even know how we did, like, crazy mechanical engineering way back in the day before we had things to help us do math. Do they teach a thinking process for making these circuits? No. Not to me. I don't know. I'm not an electrical engineer. I'm just thinking through it in my brain. Maybe they teach electrical engineers, but I got my degree in mechanical engineering. Let's just play this. Okay, so this one. So... how do we reduce the number of gates here? I think we can reduce it to an AND gate from this bottom one and this XOR, and an AND gate from these top two. That covers any pair. Yes, that covers any pair. And then we reuse this triple AND to cover all of them being on. So... that comes from... this. And this. And this comes from these two. And then these all get fed into the triple OR. Is this also correct? Okay, we've successfully reduced our number of gates down by 1. We are slightly more optimal than we were before. Is this technically 2 completely separate combination, was it combinational logic networks? Is that what the word was? Thank you for throwing stuff at me, Gojo. I don't think necessarily it is mystery. I think what I had before, where we had one set of logic that decided the carry and a completely separate set of logic that decided the sum, was 2. But what we just did now has inputs from one to the other. So I think this is now just 1. But I don't know for sure because I'm not familiar with the term and I'm not familiar with the definition. Okay. Can we make this better? Certainly we can make this better. We must be able to make this better. How many gates are there? 1, 2, 3, 4, 5, 6, 7. Can we do this with less than 7 gates? How bad is the logical effort here? I feel sort of bad because I'm pretty sure in the class that was teaching me about the delay, I'm pretty sure they went over they went over full adders. So I probably at some point learned the exact build. But I can't remember. Frick, whatever. We're accepting it. Move on to more interesting problems. You didn't understand any of the spaghetti? It's hard. True. It's hard. It's hard, and it takes a lot of thinking, and my brain go overclocky, and my head fry. You learned how to do it yesterday in class, Mystery? I'm glad what I'm talking about is, like, perfectly matched with your courses, then. The delay line is allowed to depend on its own input. This is because its input does not influence the rest of the circuit until the next tick. Square pins in the game never affect the output in the same tick. They therefore never cause circular dependencies. Output red even on the ticks and output red on the even ticks and green on the odd ticks. Okay. So we're gonna need a delay. Gotta get good at the hotkeys. How do we want to do this? We're gonna need to AND it with the input somehow. Either AND or is there another logic function? Wait, no, it's... Yeah, I think it should be and. We should not the output. Maybe. No, not the output is too quick. I need to rethink this. I need to rethink this, chat. Yeah, I think we for sure need the delay. Like I said. And I think and is maybe the right way to go. Well, not the input. So that way, one side of the and will always be on. We will... output from the and to the delay. That gives us green. Will this be on forever? No, it won't be on forever. Good. And then we need to start it off instead of on. So that'll delay it, or that'll flop it again. Let's see. Does this give us what we're looking for? Yeah! Yeah! We're the best! Hey, Snuggy Cat, how are you? We're doing some logic gate logic. With timings! With timings now, it's getting intense. It helps to break the problem down into smaller parts and add inputs incrementally. Yeah, that's absolutely what I think. Definitely I try and break down outputs too, right? If we have multiple outputs, I try and solve for one output at a time. Yeah, it's a puzzle game, Snuggy Cat. It's called Turing Complete. The idea is supposedly that you slowly build your way up from doing NAND gates to building a full complete computer processor, and I've seen it. I've seen, like, apparently people do, like, build full complete computer processors because they're building stuff in here that outputs, like, bad Apple. They're literally building computers that play memes on here. Okay. What do we got? If components output different values on the same wire, you get an error, okay? However, some components have gray output pins. These are not outputting at all when the component is not enabled. This is the case for the bit switch component. When the top pin is red, the output is disabled. This means that more than one of these gray output pins can connect to the same wire and not cause an error as long as only one of them is... Chat, these are transistors. These are the transistors in... literally the transistors we talked about in gates just now. You just turn one of them on and that connects it to high, or you turn the other one on and it connects it to low. That's like literally what you could use these for. Using 2 NOT switches and 2 switches, build an XOR gate. Okie dokie. We have 2 switches and 2 NOTs. Doom. XOR gate. So we need it to turn on when only one input is on. We talked about how the music in this game is good. It is good. It is good. What bothers me is it doesn't loop properly, so now we have a moment of freaking silence, and I'm like, should I have turned my background music back on? Okay. Whatever we do, it has to be symmetrical, because the XOR gate has inputs that are symmetrical. I'm just spitballing here. that we can do something crazy. Nope, that would be wrong. I guess it doesn't have to be symmetrical. We could use 2 NOT gates in line with each other. We do 1 NOT gate. That connects it. Somehow we need to pass... Okay, so right now that would pass 0 through. If we turn this one on, we stop passing 0 through. Catabell, huh? Nya, nya. Okay, so if the bottom one is on, we're off, we're enabling the pass from the top. Okay? If the top one is on, we should enable a pass from the bottom. Top is on, enable pass from the bottom. But we should only enable pass from the bottom when pass from the top is on. Wait, no, we can actually pass them both. We can pass them both when both are off. So maybe let's try that. Does that work? I haven't done all the computations in my head on whether this makes sense or not. Okay, it does. Yeah, so it's just a symmetrical thing. Let's clean this up. Let's clean it up, make it look prettier. So we're not super confusing. So this is the pass for the top. This is the pass for the bottom. And they are enabled by the opposites. Whoops. Boom. I guess it's still not that pretty, but it's prettier than it looked before. Do. Cha-cha-cha. Nya. Nya. We're the best. We are experimenting with how backgrounds influence cognitive functions. I hate it because it worked. I noticed the background change. I was like, that's so much prettier. When invert is green, output the opposed value of value. Otherwise, just output value as is. Okay. We need... That's XOR. Which side is invert? I think this Is this one invert? Invert is... Yeah, invert is the bottom one. Okay. So when invert is green, output the opposite of the top. Otherwise, output just the wait. Let me quickly process this. We don't have a switch here. Otherwise, the switch would be great here, right? Because then we could pass one switch through the inverter and one switch straight. And then just have the inputs of both switches as to the invert line, because that decides whether they should be on or off. I want XOR, is what my heart tells me. Because XOR will immediately flop them. The one problem is... Wait, is it actually a problem? Or is this actually the solution? Wait, yeah, isn't this actually just the solution? Chad, I'm so angry. I'm so angry. I'm so stupid. Okay, you may think it's unethical to eat all the Earthlings that don't win the competition. But it's actually is okay because you live good lives in the wild and we don't let the meat go to waste. Your mom never lets meat go to waste. Or each bit of the input bytes and output the results. Why are there 2 of each? Oh! Oh, they're buses. Okay. Chat, what are the chances that we don't need the bus and we can apply the logic to... Or, we don't need the breakout and we can just apply the logic to the whole bus? There's no way, right? That's not gonna work, right? Oh no, this clearly puts the wrong output. Yeah, okay. Well, this is gonna suck. This is gonna suck it. This is gonna suck it. This is so many... I also don't think that there is... I don't think there's necessarily a faster way to do this. Not from what I can tell about the assignment. It's literally just 8 ores. 8 ores, like we're prepping to row a rowboat. A big row-powered boat. Competitive rowing-sized boat. With 8 people? Wait, do the competitive rowing people, do they have 2 oars per person or 1 oar per person? Does anyone know? 1, 2, 3, 4, 5, 6, 7, 8. Three? Did you say 3 oars per person? Or is that an old message? Do. They have a backup? feel like you're full of shit. Why would they need multiple backups on the ship? Competitive rowing, I thought, was like teams of people. So even if you have teams of people, then you at most should have like 2 backups for the entire ship of like 8 people. Do 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 do. How are you, Ellie? How are you? We're doing crazy in the membrane stuff. Full of shit? Well, aren't we all? It just means you had a good lunch. Our previous model of brain size was being the main predictor of intelligence was naive. I feel like brain size is relevant. I feel like it is relevant. Tool making and usage is key in the early evolutionary stages of developing intelligence. Therefore, the number of arms on a creature is clearly the main predictor of its intelligence. Did you know there are sea creatures from your planet with 4 times as many arms as you, and they are doing better in tests? Wow, you bench. I'm gonna kick the shit out of you. What a meanie. Also, what a ridiculous assignment that we're literally just doing 8 knots. That's 8 knots, I think, is maybe fast for boats, by the way. Going back to our rowing conversation. How many knots do you guys think, like, professional rowers can row at? I think a knot is, like, slightly more than 1 mile per hour. Or a nautical mile is slightly more than 1 normal mile. I think it's, like, 1.15. Do. Set game turn. Ellie, thank you for reminding me. Frick. Streamer issues. Do. If any of you guys are interested in this sort of stuff, you should pick this game up, by the way. It's super fun. Thank you for the nuts, Ellie. Thank you for the nuts. Almost as many nuts as your mom gets in a night. Do. Okay, last one at this difficulty level. Add 2 input bytes. Each output bit in the other output should be a result of the addition of the corresponding... Guys, can you freaking... Also, wait. Wait a second. You guys... Well, this is awkward. I didn't realize that you guys can't see the sub-windows in these. Oh, now you can. Weird. Eh? Hold up. Okay, you can see him now. What the heck's going on with my OBS? Okay. 2 input bytes. Each output bit in the output should be a result of the addition of the corresponding bits from the inputs and a potential carry. So this is actual addition. That's broken up into each of the freaking bits. Okay. Do we have the full adder? Oh, we do have the full adder. Thank freaking God. We have... This is actually gonna be so intense. Very, very intense. Okay, so our sum will be this. This will be our ones adding. Oh no, I can already see this going so terribly. This is gonna get so freaking messy, guys. Alright, we need to plan better. We need to put things in better positions before we start building. Before this turns into something truly awful. Okay. Marginally better. We should also put this in a better position. Okay, so this is how computer adding works. It's literally freaking this. It's a bunch of full adders, one for each bit. With the carry input for the full adder being from the output of the previous bit. Is the carry output of the previous bit. Oh man, we're cooked. We're cooked. Do 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 do. Need to do 3 more of these? Oh man. Man. Do. I hope I selected the right outputs on these adders. It would really suck if I mixed up the sum and the carry outputs of each of these adders. Guess we'll see in a second. So far, looking good. We're the best. We're the best. This wasn't even that difficult. It was just really tedious. Okay. More difficult problems, please. I want to think. I want thought-provoking problems. To know the difference between things, you need subtraction. To get subtraction, first you need negative numbers. This level introduces 2's complement, the most common representation for negative numbers.
Thought-provoking.
Your mom provokes. That's a thought-provoking. 2's complement, the most common representation for negative numbers. Here, the highest digit is negated For bytes, this means the 8th digit changes its value from 128 to negative 128. You finish this level when you get to level 3 or beyond. So this is a speed round adding situation. This is gonna fucking suck. 1 sign in binary, 1. 15 is everything before 16. Negative 1 is, oh god. Everything on, everything on, everything on. Negative 2. Negative 3. What? 1 sign in binary. 15 is everything up till 16. Negative 1 is everything turned on, including the negative 128. Negative 2 is everything turned on except for the... yeah. Okay. How does this work? Shit. 1 is 1. 15 is everything up to 16. Negative 1 is everything including negative 128. Negative 2 is... oh, okay. Negative 3 is... that. Negative 14... this. Negative 7... 12... Frick! We're gonna be so bad at this! We're gonna be so bad at this! Negative 1. Negative 2. Negative 3. Negative 13 would be negative 12, which is these two. Okay, negative 2 is... those. Okay, negative 15 is 14, which is this. Okay, I'm getting the hang of it. It would be... Frick! Okay, so when we do negative... chat, I found the cheat code. When we need negative, it's bring it 1 closer to 0. So if it was negative 7, it's negative 6. And then do the invert of the positive. Okay? Invert of the positive for what it would be if it was 1 closer to 0. So 1, that's positive, so that's 1. Negative 1. All of these. Negative 2 would be negative 1, which would be inverted like that. Negative 3 would be negative 2, which is inverted like that. Negative 6 would be negative 5, which is inverted like... oh god. This. Negative 2, which is inverted like this. Negative 5, which is inverted like this. Yeah? Okay. We're battling, chat. We are battling our inner demons. Negative 1, boom, 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 boom. What? I'm no longer qualified to make fun of Gura not being able to add negative numbers, I guess. Negative 3 goes to negative 2, which is boom. Negative 4, negative 3, boom. Negative 16, and negative 15, which is this. Negative 4, which is negative 3, which is this. Negative 3, negative 2 is this. Negative 6 turns into negative 5, which is this. Negative 15 turns into negative 14, which is this. Negative 1 is everything. Negative 8 turns into negative 7, which is this. Negative 7 turns into negative 6, which is this. Negative 11 turns into negative 10, which is this. Negative 7 turns into negative 6, which is this. Negative 15 turns into negative 14, which is this. Negative 19 turns into negative 18, which is this. Negative 16 turns into negative 15, which is this. Negative 8 turns into negative 7, which is this. Negative 58 is... oh, God. I tried, chat. It burned my brain. It burned my freaking brain. But we at least beat the requirement to end the level. Flip the bits and add one. Okay. Yeah. You need me to do your homework? No. No, you need to do your own homework. Okay? You need to... Belle's brain isn't meant for high-level computing for longer than, like, a couple minutes. The overclock went hard. It's due in 30 minutes? Frick! Well, you better work hard then. We can work together, because my stream's supposed to last 30 more minutes too. To go between negative and positive, you flip all the bits and add one. Okay. Last bit is green. The value is always negative. And flip all the bits and add one. So negative 1 would be that. Wait. Okay. Alright, this is gonna be difficult. This is gonna be difficult. Even though he did not pass our tests, we decided to keep the dog. Unlike most Earthlings, he is fluffy and follows simple instruction well. So does your mom. She is fluffy, and whenever I tell her to do something, she does it. Even though he did not pass our test, we decided we might want to team you two up since you complement each other's shortcomings so well. That's so mean. That's so mean. When the bit selector input is red, output byte E, output byte A. God, I can't even read. My brain is fried. Otherwise, output byte B. Okay. That, seems reasonable, except that I don't really want to break these bytes out. Like, at all. Wait, can we use a switch? Can we use the switch on the bus lines? We can use the switch on the bus line. Okay, that actually makes it easy. Okay, so A is the one we want to output always. Or output, you know, normally. So that's going to have a not from our invert line. And then B is the one that we want to output when our invert line is on. That's gonna get it straight from the invert line. Boom. I think. Does this work? Easy, chat. Easy. I'm so glad we have 8-bit switches. It would have really sucked if I had to build freaking switches for each individual bit on the byte. On the nibble. Frick, so many words. Alright. Take the input as signed, where the 8th bit is negative 128. Make a component that takes a number and negates it. For example, 4 negated would become negative 4. 9 negated would become 9. Okie dokie. So if we remember how we negate things is we flip all the bits. Plus 220. Okay. We flip all the bits and then add 1. Does that mean we just don't flip the... Does that mean we just don't flip the 1? That's a lot of knots. It's really naughty. Do, 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 do. I wonder if completing this could be like something you could put on your resume. Do, do, do. Something about this seems wrong. This definitely seems wrong, but I don't know what's wrong with it yet. Okay. So... Okay, 1 times 0. Flip all the bits. Don't tell me we have to do an adder. Don't tell me we have to do a bunch of full adders. If we have to do a bunch of full adders, I'm gonna be sad. Bum. Bum, bum, bum. Okay, I see. So if we literally just do... Oh, I didn't even realize we had... Frick, I'm dumb. I didn't even realize we had 8-bit NOT gates, which is pretty sick. Which means we can clear all this garbage. Make an 8-bit NOT gate. And an 8-bit add gate. And then where do we get a 1? We break it out? break it out like that, and then we pull a 1 from... I'm so confused. Where do we pull the 1 from? Excuse me. Does this work? No? Okay. So we need a 1. An on to add to this adder. We're adding a -1 and a... Okay. How do we flip something to negative? Chat. Add 1. Can we do a normal... Do we have half adders? No. Great. Check your single bit components. That makes, like... What I'm thinking is what we could do is we could do the whole breakout thing and do literally add... Oh, there's on. Okay. Is that it then? Okay. Thank you, Lusting Asmodeus. I was actually struggling because I didn't realize there was an on. I didn't even need this bus. Frick. But I'm happy about it. Happy we can be done with this garbage. Thank you. Okay. This level has 2-byte inputs and 2-byte outputs. Your goal is to copy from one of the inputs to one of the outputs. The first bit input determines which input you should copy from. The second bit input determines which output you should copy to. Okay, so we want switches. There's a brute force method to do this, which is to use AND switches for the input slider, the input selector and the output selector. Make sets of them to choose every combination. That might actually be the legitimate way to do it. Oh, interesting. Okay, we're limited on what we have. Okay. That actually makes it way more straightforward, I think. Okay, so... First one, I assume means... Okay, that sets us up to pull from the correct input, because when input selector is off, then we will always pull from the first. Now, given both of these, now we need to do the same thing with the outputs. I think output selector, when it's off, means we should go to the first one. That makes sense in my brain, which means we need a NOT. And then when it's on, it should go to the second one. Okay, does this work out? Heckin' yeah! Heckin' yeah! We're just using gates to pass it through from whichever one we want. Pretty cool stuff. The delay line only allows us to save value for one tick, but sometimes a component that can save a value for longer periods of time is useful. We want you to build such a component. So is this memory, or it's just longer delay? You have two inputs. When the first input is green, update the saved value. The second input is the value. Wait. When the first input is green, update the saved value. When the second input is the value. Okay. Always output what is currently saved. This is the diagram of the component we want you to build. Save and name, okay. Okay, so what we need is we need memory. Memory comes from... memory is built. CMOS memory is built from two inverters that feed each other, but I don't know if... I thought there were problems with... Yeah, circular dependency. Okay. So... let's see. How do we get something to keep itself? It needs to have some sort of... It is memory, yeah. But how do we build it with what we have? We need something circular so that it can have positive feedback on itself, but only when save enable is off. But in order for it to be circular, we need delay. We have a switch. Okay. Here's the game plan. We're going to have something circular with itself that is only enabled... It is only enabled to be circular when save is disabled. That comes from a NOT. And that enables the circularness. When we enable, what feeds it is not itself. What feeds it is the input. The question is, where's the output? Output is 1 delayed. One delayed at the value. Can we delete this? Is it just this? Is that all we need? Yeah, that is all we need. Okay. I mean, I prefer the idea of the CMOS memory. Like, I sort of like that better, where you have the X and the not X, and they invert each other, and that sort of sustains itself. But I understand where the helpfulness of this has its architecture. Create a circuit that can save or load a byte. Oh, did you? Lusting, did you have like a crazy solution? How long ago did you play this game? Create a circuit that can save or load a byte. When the first input bit is load, when the first input is green, load the memory and send it to the output. When the second input is save, input the byte. The output has an enable pin. Enable it only on load. Okay, I'm going to struggle to follow these instructions, but mainly because I'm trying to... Internalizing these instructions to remember them will be... You made a flip-flop? Okay. Yeah, because... That makes sense. But I think the flip-flop part of it is that you can't save and load... You're not supposed to save and load at the same time. Those two should be enabled opposite. I don't know if that's necessarily true from these instructions. It doesn't say in these instructions whether you can save and load at the same time. But we'll see. Alright, so we'll start by 8-bit. Do we have 8-bit memory built? We have an 8-bit mux to choose. Okay. Interesting. So 8-bit mux means... Whoa. My brain is frying just thinking about the concept of the problem. Been about a year since you last played it. Did you beat it, Lusting? You probably beat it if you haven't played in a year. I think this game is interesting enough that I want to finish it relatively in the same time. Wait, was there two? No, there's only one input, right? Where are the instructions? Shit. Create a circuit that can save and load a byte. When the first input is load, is green, load the memory and send it to output. And the second input is... Okay, so the first one is to the output. This guy is a switch to the output. Do. What are these? And the second one is input, which means that's our switch here. Is this just... Do we have memory now? We do have memory. Okay. Do we have multi-bit memory? We don't have... Wait, we... So we have to do individual bits of memory? Well, that sucketh. If that's the case, then we don't need... I don't think we need a switch to enable input. It should just be a bunch of 1-bit memories. I think. Got up to the assembly challenges. I look forward to whatever crazy stuff I'm going to have to do in the future. This is already relatively taxing on my brain. 6, wait. There's the faster way to put these down, which is to hold, I think. Something like that. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay. The fan out on this input is massive. Massive fan out on this one save. That's not good. That's a lot of capacitance. Look at all those wires. Also, this would not surprise me if I've done this wrong. Wait. 1, 2, 3, 4. We fucked something up, chat. We fucked something up. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Oh! Okay. That scared me. That scared me for a second. I was like, why do we have different numbers? And for you, for some reason, are not connected. This is nasty, though. This is so gross looking. The second pin on output is an enable switch. I need the instructions again. Where's the instructions? Create a circuit that can save or load a byte. When the first input is green, load the memory and send it to output. When the second input is green, save the input byte. Enable the output pin. Oh! Okay. So we just don't need this switch then. I guess? Yeah, okay. So we have something where our state should be... Wait, what? I'm so freaking confused. Why does that count when it says desired state is 255, desired output is 0? Did I do it right or did I do it wrong? I'm so confused. I'm so confused. I think what I did was right, but what it said at the bottom where it's like desired state and desired output did not look right. Okay. Create a component that can switch a signal between 2 pins. Yeah. Isn't that... I'm confused. I feel like I have not enough... Oh, it's from an on, I guess. Isn't that just a switch? Sorry. It's you. 2 switches. One will be for... Okay, when the input is off, it should just pass through to top. That's easy, that's a not. And then when it's on, it should switch it to send to the bottom. That's... oddly simple compared to what we just did, but okay. With the 3 bits of input, there are 8 combinations. Make a circuit that selects 1 output for each of the 8 combinations. No more or less than 1 bit should be green at a time. Make 3 bits of input, 8 combinations. That's... yes, that's the 1 bit, the 2 bit, and the 4 bit. Which total do 0 through 7. Okay. Make a circuit that selects 1 output for each of the combinations, no more or less than... okay. So... I can do the last level with just 1 NOT gate? Wait. This level. This level? Oh, I guess you use the NOT gate to feed. Yeah, okay, that makes sense. Interesting. With 3 bits of input, there are 8 combinations. Make a circuit. Okay. So every combination needs to light a different... okay. There is a way to do this with an absolute... no, actually there's a way to do this without that much. Okay, we need triple ands. This is how... this is a decoder for memory. Normally these are made with... sorry. Brain shutting off as I gather more parts. 1, 2, 3, 4, 5, 6, 7, 8. You make these by having every combination of a signal and it's not. So that's the 1 bit and it's not. Here's the 2 bit and it's not. And here's the 3 bit and it's not. I probably should have done the knots on the bottom, but it is what it is. 1, 2, 3. Okay, so, and that's all of them off should lead to the first bit. only the first one on should lead to the second, so that's the first one on, and then the knots of the second and third. Oh, this is ugly. The third one should light when only the second one is on. So that is the second one and the knots of the first and third. This is ugly. This is ugly. But this is actually, I mean, they do this in stages in real life. It's a pre-decode and normal decode, but here we'll just do it in one single big decode. Fourth one lights when first and second are on. First and second, and not third. Fifth one lights when only third is on. That's not from the first and not from the second, and actual from the third. Do 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 do. Hey Ash, how are you? How are you? This is 6-1, right? 6-1 lights when first is on, second is off, and third is on. I hope you're enjoying your tea. I hope you're enjoying your tea. I hope you're ready to share. I hope you brought enough for the class. 7th one is on when third and second pin are off. Or are on, but first pin is off. And last one is when all are on. Easy. Easy single stage decoder. It's only super painful to look at. From the eyes. Alright, let's see. Wait. We messed up one of them. 7? 7 is... come from... Oh, it's not freaking... connected? What did we... Why did we have just floating inputs? You did bring enough? Wait, and you ate ice... You ate ice cream with that? What flavor was it? I hope it was good. Easy. Easy. You had intern add a disable bit to this component. We were tired of looking at him running in circles, and we were looking for other pointless and tedious tasks to gift him. 3-bit decoder. Easy. Oh! Would you look at that? Would you look at that? It's 9 p.m., chat. That means it's time to end stream because I have to prep for Betty bed and then work tomorrow. But we have Twitchcon this weekend, so I won't be streaming this weekend. And then I'm on work travel next week until Friday, so I probably won't be streaming until next week's Friday. But I hope you guys have a good time without me till then. I hope you guys have a good time without me till then. Try not to miss me too much. Try not to miss me too much. You hope I have a good TwitchCon? Thanks. Thanks. I have no idea what I'll be doing there yet. I did not have a game plan. Maybe I should have done a planning stream. But it'll be you. Are you gonna be there? Do I have to wear a disguise so I won't be recognized? You wish? Shame. Shame. Alright, well, thank you guys for watching. I hope you had a good night. I had fun. I hope you maybe learned something, or maybe not. Maybe you're just here for the vibe. Maybe you're just here for the vibe. But I had a good time, and I hope you guys had a good time. And I'll see you guys next time, which is not for another week and a half till Friday next week. Friday next week. But have a good one. Have a good one. Bye-bye. Bye-bye. Boom. Thanks for hanging out.